Welcome you all to the lecture number 3 of week 1. As a quick recap, in the last lecture, that is lecture number 2, we started our discussion with the octal and hexadecimal number system and their conversion. From there, we moved on to the discussion onto the binary arithmetics and how addition, subtraction, multiplication, division is performed in binary number system. The lecture session also discussed in brief the ones and twos complement to perform binary subtraction. Today, we will begin our lecture session by discussing some of the questions of practice problem 1. The question is a binary number with n bits with all bits 1 as the value. Assume let the number of bits is equal to 4, that is n is equal to 4. So, we have got 4 columns starting with the least significant bit to the most significant bit. The least significant bit has a position weight of 2 raised to 0, followed by 2 raised to 1, 2 raised to 2, and the most significant bit has the positional weight 2 raised to 3. And the bit values as given in the question should all be equal to 1. Now, the next step is to multiply each bit value with its corresponding positional weight. So, we will start with the most significant bit, that is 1 into 2 raised to 3, which is 8, plus 1 into 2 raised to 2, that is 4, that is 8 plus 4 12, plus 1 into 2 raised to 1, that is 12 plus 2 14, plus 1 into 2 raised to 0, that is 14 plus 1 15. The value is 15. Or we can generalize for an n bit number. If all the bit values are 1, that means each bit position occupies the binary bit 1, then the value of the n bit number is 2 raised to n, where small n stands for the number of bits minus 1. Now, we will go to the next question. The number of bits required to represent the decimal number 40. Again, we will assume let the number of bits is equal to 4, that is small n is equal to 4, and we know all the positional weights starting from the least significant bit, that is the bit that is the positional weight is 2 raised to 0, and going up to the most significant bit where the positional weight is 2 raised to 3. Now, we assign all the bit values as the binary number 0, and as discussed in the previous question, if we multiply the bit value with its corresponding positional weight, we know that 0 into 2 raised to 3, that is 0 into 8 is 0, plus 0 into 2 raised to 2, that is 0 into 4 is again 0, plus 0 into 2 raised to 1, that is again 0, and 0 into 2 raised to 0 is again 0, and if we add up, it will come to 0. Similarly, if all the bit values are equal to 1, then we have seen that the corresponding decimal value will be 15. Therefore, we can generalize for an n bit number, the decimal value it can represent is between 0 and 2 raised to minus 1. Therefore, to represent our decimal number 40, we require 6 bits, that is 2 raised to 6. What is 2 raised to 6? That is 64 minus 1, that is 63. So, if we have got 6 bits, we can represent a decimal number between 0 and 63. Now, moving on to the next question. The value of base b if 128 number given in decimal number system equals to 204 with the base or radix is unknown, which is given as b. So, we all know how to convert a binary number to a decimal number system. So, what we do that in a binary number, we multiply the bit value with the corresponding positional weight. So, here also the number, that is 204 with the base as b, will multiply it by the positional weight. So, that is it has got 3 values, 3 digits. So, 2 into the positional weight, that is b square, plus 0 into the positional weight, that is b raised to 1, plus 4 into b raised to 0. So, which comes out to be 2 b square plus 4 equals to 128. Now, we do the arithmetic manipulation, we get it as 2 b square is equal to 128 minus 4, that is equal to 124, or b square is equal to 62, or b is equal to 7.87, or we can say that the value of base b is equal to 8, or it is an octal number system. Next question, convert the following octal number, that is 256, to hexadecimal number system. In the previous class, that is lecture number 2, we discussed that to convert any number system, that is the octal number system or the hexadecimal number system, it is better to first convert to the binary number system. And we have also discussed how to represent an octal number system in binary number system, that is by clubbing 3 bits starting from the rightmost octal digit and then moving on to the leftmost octal digit. So, we have got 256. So, first the rightmost octal digit is 6, we will represent it by 3 binary bit numbers, that is 110, followed by 5, which is represented as 101. Similarly, the octal number 2 we represent it as 010. Our question is to convert the octal number to hexadecimal number. So, what we have done, we have already converted the octal number to the binary number. Now, we will convert the binary number to the hexadecimal number. Here what we have to do? We have to group it into 4 bits. So, what we have done? We have grouped the 4 bits starting from the leftmost bit. We have got 110, we have grouped into 1, and then 1010, we are grouped into another 4 bits, and the most significant bit is 0. So, now we are clubbed into 4 bits each. So, 1110 in hexadecimal represents the hexadecimal number E, and 1010 it represents the hexadecimal number A. Therefore, the conversion of the octal number to the hexadecimal number system is AE. Now, we will move on to the another question, multiply the following octal number 46 into 4. So, first we will convert 46, that is the octal number, to its equivalent binary number. So, we will use the same conversion principle as we discussed earlier. So, both the multiplicand and multiplier we have converted into the equivalent binary number, and we multiply these two numbers following the binary multiplication rule. So, we will get the final result as you have seen it. We multiply it starting from the multiplier with the leftmost significant bit, and then we shift it towards the left by 1 bit, and we get the final answer. And the final answer which we get now, it is in binary form, but we need our multiplication and the result in octal form. So, what we will do? Again we will convert this binary number which we got to the octal number by clubbing 3 bits starting with the leftmost significant bit as shown. So, we have got 100, which is the number 4, then we have got 001, that is the number 1, and 011, that is the octal number 3. So, we have got 314 as the final result of multiplying the two octal numbers as 314 in octal number system. Now, we will go to the practice problem 2. The first question is, when two n bits are multiplied, the product will contain maximum how many bits? That is the question. The answer is, the maximum number of bits of the result will be 2 into n. The next question, list the 3 methods to convert a binary number to its 2's complement form. So, we will start with, let the number be n. Take the 1's complement of the number, that is n star is equal to 2 raised to n minus 1 minus n, where small n is the number of bits of the number n, which is denoted by capital N. So, once you have taken the 1's complement, of the given number, then add the binary bit 1 to the least significant bit of the 1's complement which you have obtained. This is one way of getting the 2's complement of a number. The second method is, let the number be n, that is capital N, I am denoting it. Take the 2's complement of the number, that is capital N with asterisk, that is equal to 2 raised to n minus n, where small n stands for the number of bits of the number capital N. So, this is one way of getting the 2's complement of a binary number. The third method is that let the number be n. For observe the bit position of number n whose bit value is 1, starting with the least significant bit. That means, starting with the least significant bit, you have to observe which bit value is equal to 1. So, once you observe that bit value equals to 1, the second step is to complement every remaining bit after you observe the bit number 1 up to the most significant bit. That means, if you have got the bit 1, then after that bit 1 you have to complement every remaining bit. This process you should continue up to the most significant bit. Now, one more question, divide 145, the decimal number 145 by 11, that is the dividend is 145 and the divisor is 11 in binary. So, first we have to convert the decimal number 145 to binary. So, how we can do it? How many bits are required? You require 8 bits. You starting with the positional value as 1, then 2, then 4, 8, 16, 32, then 64 and then 128. That is the most significant bit, positional value is 128. So, you have got the number 145. So, you put a bit value 1 in the most significant bit. If you put a bit value 1 in the most significant bit, its weight will be what? How much? 1 into 2 raised to 7, that is 1 into 128 will give you 128. Subtract this 128, that is the decimal number 128 from 145. The balance or the answer is 17. Now, you put another bit value equals to 1 in the positional weight which is 2 raised to 4. So, now 1 into 2 raised to 4 will give you how much? It is 16. So, 17, that is the result you obtain after subtracting 145 from 128, you got 17. Now, you subtract 16 from 17, you will get a value equals to 1. Now, put one more bit value 1 in the 1's position, that is 2 raised to 0. So, the final conversion of the decimal number 145 to binary is 10010001. Similarly, you go for the conversion of the decimal number 11 to binary, which you get as 1011. Follow the same procedure. Now, we will go for the division. So, we have got the dividend as 1001 followed by 3 zeros 1 and the divisor as 1011. So, we will go for the division. So, we first multiply it by 1. So, you put 1011, then you subtract it, you get an answer, that is 1110. Go for the binary subtraction and again then multiply it the divisor by 1. So, you get 1001, subtract it, you get it as 01101. You have taken 01 from the dividend. So, you have to put a 0 here and again then multiply it, that is 1011 you will get, and the remainder you observe it is coming to 10. So, finally, the quotient which you have got is 1101, which is the decimal number 13 and the remainder, that is the binary number 10, that is equal to the decimal number 2. Therefore, we divide 145 by 11, we get 13 as the quotient and 2 as the remainder. Now, we will move on to the next topic, that is signed binary numbers. In normal arithmetic, a positive and negative number is represented by a plus and a minus sign. Normally, if we write it with pen and pencil in a paper, to represent a positive number, we will put a plus sign, and to represent a negative number, we put a minus sign. In binary number system, the leftmost bit or the most significant bit represents the sign bit, and the remaining bits represents the magnitude. The convention is to make the sign bit 0 for a positive binary number and sign bit as 1 for a negative binary number. The most common method to represent negative binary numbers are the sign magnitude 1's complement and 2's complement. So, we will go with the sign how to represent a number using the sign magnitude representation. In an n bit sign and magnitude number system, the leftmost significant bit represents the sign bit and the remaining bits, that is n minus 1 bits, represents the magnitude. Suppose I have to represent a decimal number plus 31. So, how we will go for it? The most significant bit we put this, that is the sign bit, being a positive decimal number in binary form, we will represent that with the bit 0, and the remaining bits, that is the 7 bits, will represent the magnitude of the decimal number 31. Similarly, to represent the decimal number minus 31, what we will do? The most significant bit being minus, we will put the sign bit as 1 to represent that the number is a negative number, and the remaining n minus 1 bits represents the magnitude of 31, that is the decimal number 31. Now, we go to the signs complement system, starting with signs 1 complement representation. How we go about it is obtained by taking the complement of all the bits including the sign bit of a positive number expressed in sign magnitude form. So, first we have to express the given number in sign magnitude form and then take the 1's complement. Fine. For the sign magnitude and signs 1 complement system, the numbers in the range minus 2 raised to n minus 1, where the letter n is in small, that is small n, 2 raised to n minus 1 within brackets, to plus 2 raised to n minus 1 can be represented with positive 0 and negative 0. Now, we will come to the signs 2's complement representation, obtained by taking the 2's complement of all the bits including the sign bit of a positive number expressed in sign magnitude form. Here, it shows how the decimal number minus 31 is represented in 2's complement form. So, we can see that the most significant bit, that is the sign bit, is 1, it shows that the number is negative. Here a table is shown where the decimal number 0 to 7, that is plus 0 to plus 7, and the negative decimal number starting with again with 0 to 8, that is 0 to 8 with the negative sign. How it is represented in the 3 forms, that is the sign magnitude form, the sign 1's complement form and the sign 2's complement form. So, we can see that in 1's complement form and in sign magnitude form, the decimal number 0 is represented as, you can see that 0 in sign magnitude form, it is represented as, you can see that the most significant bit has a bit value equals to 1, shows that the number is negative, and what is that number? It is minus 0. Similarly, in 1's complement form, you can see that the number minus 0 is represented as 1 1 1 1, whereas in 2's complement form, the plus 0 and minus 0 are represented as 0 0 0 0. Now, we can see that in representing the decimal number minus 8, the sign magnitude representation or in 1's complement form, it is not possible, because the decimal number 8 has got 4 bit positions to represent the decimal number 8, that is 1 0 0 0, and to represent minus 8 you need one more bit, that is you require 5 bits to represent the decimal number minus 8 in sign magnitude form. So, therefore, it is not possible to represent minus 8 using 4 bit in sign magnitude form. The same argument comes to represent minus 8 in 1's complement also. Fine, but minus 8 you can represent in 2's complement form as 1 0 0 0. So, therefore, what we have seen in this table, we have represented the decimal number 0 to 7, the positive 0 to plus 7, similarly minus 0 to minus 8 using 4 bits in all the 3 forms, that is the sign magnitude form, the 1's complement form and the 2's complement form. To sum it up, we can say that the positive number in all the 3 representations are identical with the leftmost bit 0, that is the sign bit as 0. And second conclusion is that all negative numbers have the leftmost bit equal to 1. Then the sign 2's complement have only one representation for 0. There is no minus 0 in 2's complement representation. The sign magnitude and 1's complement has 2 representation of the decimal number 0, that is plus 0 and minus 0. Now, we will do some review questions. We will start with the first question. Subtraction in a decimal number system can be done by, there are 4 options. The first option is 1's and 2's complement, second is 7's and 8's complement, third is 15's and 16's complement, and the last is 9's and 10's complement. So, you know that we have got the decimal number system and the r's complement or the b's complement, that is r, that is the base is 10 in a decimal number system. Therefore, we have got the 10's complement and the r minus 1 complement, that is 10 minus 1, that is the 9's complement. Therefore, in a decimal number system, the subtraction is done by the 9's complement and the 10's complement, and therefore, the answer is the last option, that is D. Now, moving on to the next question. The most significant bit of a signed binary number indicates what? The options are magnitude, sign, 1's complement or 2's complement. So, we know that in a signed binary number, the most significant bit indicates the sign of that particular number. If it is positive, we represent by 0, and if it is negative, we represent it by 1. Therefore, the right option is B. If the word length is 4 bits including sign bit, what decimal number does binary number 1000 represents in a sign magnitude form? So, we know that in signed magnitude representation, the most significant bit indicates the sign, it is minus 0. Therefore, the correct option is B. If the word length is 4 bits including sign bit, what decimal number does binary number 100 represents in 1's complement form? Fine. So, it represents in 1's complement, we have got 4 bits. So, in 1's complement form, we can represent a negative number minus 2 raised to n minus 1, that is 2 raised to n minus 1, that is 4 bits, that is 2 cube minus 1, that is minus 7, to 2 raised to n minus 1, 1, that is again 2 cube, that is 2 cube is 8, 8 minus 1, 7, that is you can represent in 1's complement using 4 bits from minus 7 to plus 7. So, here the given number is 1 0 0 0. Therefore, it represents the decimal number 7 with the sign as minus, that is minus 7. Therefore, the right answer is option A. The next question, if the word length is 4 bits including sign bit, what decimal number does binary number 1000 represent in 2's complement? So, in 2's complement, using 4 bits we can represent minus 2 raised to n minus 1, that is minus 2 raised to n minus 1, where n is the number of bits, that is 4. So, minus 2 raised to n minus 1 minus 2 cube, which represents minus 8, to plus 2 raised to n minus 1 minus 1, that is 2 cube 8 minus 1, that is 7. That means, you can represent a decimal number between minus 8 to plus 7. Therefore, we are here using 4 bits. So, it represents the decimal number 8 and with the negative sign. Therefore, the right answer is option D. The minimum number of bits required to represent a positive decimal number in the range 0 to 127 using 2's complement representation is. That means, if I use 7 bits, to 2 raised to 7 minus 1, that means 2 raised to 6, that is 2 raised to 6 is 64 minus 1, that comes to 63. Therefore, I cannot represent the decimal number 127. So, I need 8 bits. So, 8 bits will be 2 raised to 8 minus 1, that is 2 raised to 7 minus 1. Okay. So, 2 raised to 7 is 128, 128 minus 1 is 127. Therefore, the right answer is option C, 8 bits. Now, as an exercise, I have given you a question, perform the following operation on decimal number using 2's complement. You have got 4 questions, the decimal number 32 minus 21, then 21 minus 32, then 32 minus of minus 21, and question D is minus 32 minus 21. So, you have to perform the subtraction operation using 2's complement. So, you have got the first question, that is question A is 32 minus 21. So, first we have to represent the positive decimal number 32 in 8 bits sign 2's complement representation, which is given as 0 0 1 0 0 0 0 0, and you have to represent the decimal number 21, that is minus 21, in 2's complement representation. So, first we will represent the decimal number plus 21 in sign magnitude form, which comes to be 0 0 0 1 0 1 0 1. Then you have to convert into 2's complement. So, as discussed earlier, using the method number 3 in one of the practice problems, the least significant bit is 1, and once you observe the bit value 1, then you have to complement the remaining bits. From this we have seen that the least significant bit value itself is 1. So, then we have to complement all other bits after that. So, we start with the next, that is 0, we complement, that is 1, then 1 complement to 0, 0 complement 1, 1 we complement, we get 0, 0 again complement, we get 1, 0 again we complement 1, and the most significant bit 0, again we complement it, we get 1. So, this is representation of minus 21 in 2's complement form. Now, our question is 32 minus 21. So, we can write it in this form, that is equal to 32 plus of minus 21, because minus 21 we have already represented in 2's complement form. So, now we add it to the decimal number 32, and we get the result as, starting with the least significant bit, 1 1 0 1 0 0 0 0 with a carryover from the most significant bit, that is 1. So, you neglect the carry and the final result is positive, and what is that value? That is the decimal number 11. Now, come to the second question. Here the question is 21 minus 32. That means, the subtract is greater than the minute. So, as we have done earlier, represent your decimal number 21 in 8-bit sign 2's complement representation, and we get it as 0, 0, 0, 1, 0, 1, 0, 1 with the most significant bit as 0 and the least significant bit as 1. Now, we will represent minus 32 in 8-bit sign 2's complement representation. We know that first we represent the positive number 31 in sign magnitude form. So, we get it as 0, 0, 1, 0, 0, 0, 0, 0 and convert it into 2's complement form. We have to observe the bit value 1. So, you have seen that you get the first one and after that you complement. So, we complement 0, we got 1, again we complemented 0, we got 1. So, therefore, minus 32 in 8-bit signs 2's complement representation is 1, 1, 1 followed by 0, 0, 0, 0, 0. Now, we add this 2's complement of minus 32 with 21 and you get the answer as 1, 1, 1, 1, 0, 1, 0, 1. So, here we have seen that there is no carryover or carry generated from the most significant bit, and we have seen that the most significant bit has a value, bit value equals to 1. Therefore, the result is negative and it is in 2's complement form. Again takes the 2's complement of the result which you obtained to get the final result. Similarly, you can go for 32 minus of minus 21. Here minus 21 we represent in 2's complement form. So, therefore, it will becomes equals to 32 plus of plus 21 and here you got the answer as 0, 0, 1, 1, 0, 1, 0, 1. So, what is 32 plus 21? That is positive number 53. The last is minus 32 minus of plus 21. So, you can represent it as minus 32 plus within bracket minus 21. So, you take the 2's complement of the decimal number minus 32 and take the 2's complement of the decimal number minus 21, that is the subtract, and now you go for the addition. To get the final result as starting with the least significant bit 1, then 0, 1, 0, 0, 1, 1 with a carryover as 1. So, you have to neglect this carryover as the most significant bit value is 1, it is in 2's complement form and again take the complement to get the final answer which is minus 53. To sum it up, the operands if of the opposite sign, the results are obtained by following either 1's complement or 2's complement for subtraction. The second conclusion is that the operands if of the same sign, then check the most significant bit, that is the sign bit of the result, and compare it with the sign bit of the operands. If the signs are same, then the result is correct and is in 2's complement form. If the sign bit of the result is different from the sign bit of the operands which are same, there is a problem of overflow and the result has to be interpreted accordingly. Hope you had a good understanding on the different arithmetic operation performed in binary number system by watching this video. Thank you and see you all in the next lecture. Until then, practice the problems given as practice 3. We will be solving some of the questions of it in the next lecture.